So there's this phrase that I actually say quite a lot every day and in my research, and it's that there is a supermassive black hole in the center of every galaxy. And it's so casual when I say it, and it's so throwaway, but I kind of forget there's like 100 years worth of research and results from experimental studies that are observational and theoretical results and computer simulations that all jigsaw puzzle piece together to make this big picture of the universe that we live in that allows me to say that so casually. And I used to hate that at school, how you were just taught facts. You were never taught how we actually figured out the facts and how many different results had to come together for us to understand something. So I figure it's about time we change that. So our story starts in 1909, with a guy called Faith, who was at the Lick Observatory in San Jose in California, and he was using a telescope there to look at spiral nebula. Now, nebula back then was just sort of a word that was used to describe anything that didn't look like a star. So it was sort of gassy and dusty and just fuzzy on the sky, really. Whereas now we know that what they termed nebula for everything, we know that nebula are things in our own Milky Way. They're either the sort of areas where a star has died or they're areas where stars are being born. Whereas galaxies are actually outside our own galaxy, the Milky Way. They're islands and cities of stars in their own right, containing like 1 billion stars. And so what Faith was looking at, but he didn't realise, was galaxies. And he was trying to work out whether they looked like other nebula or whether the spiral-shaped nebula were any different. And when he took the light from those nebula and split them through a spectrum and sort of got a graph of how much light was at all the different colours and wavelengths, he found that 5 of them looked like they were actually a collection of stars, rather than what had been seen for nebula, which was emission lines. Whereas for the 6th one, he saw what looked like a collection of stars, but also with emission lines. Now, emission lines on a spectrum mean that you've got elements of material that are giving out light at a very specific wavelength. And that's caused by the fact that you get light from an energy source shining on, like, say, hydrogen gas, that then causes the electrons around that hydrogen gas to jump up to the next energy level where they could live. Then they're sort of not supposed to be there, so they drop back down, and when they drop, they give out a very specific wavelength of light. And so that had been seen in normal nebula because the source of energy there was either stars that had died or stars that were being born. What Faith didn't know is that what he'd seen in this 6th spiral nebula was actually emission lines caused by the active supermassive black hole that was in the center of that galaxy. When I say active, I mean that it was accreting material. It was sort of spiraling in material to itself and growing in mass and giving out energy that it then ionized the surrounding gas with. So the reason that Faith, didn't know that's what he was looking at was because A, we didn't know galaxies existed back then. The size of the universe was considered basically the furthest star away in the Milky Way. And B, we didn't know that black holes existed either. They were considered kind of a hypothetical object. They were first proposed, or the idea was, back in sort of 1784 by an English guy called Mitchell. And he proposed this idea of an object so dense that the escape velocity that you would need to get off that object would be greater than the speed of light. But all through the 19th century, physicists considered light to be a wave and therefore unaffected by gravity. And so that idea of this object that was that dense was sort of ignored for a really long time. That is, until Einstein came along. So Einstein in 1915 released his theory of general relativity, and that got us thinking about gravity in a completely different way. He said, imagine that the entire universe is made up of this fabric of space-time. So the way that the human brain can picture that, if you imagine sort of like a bed sheet stretched taut, and then you put something like a basketball in the middle of that sheet, you're going to then sort of curve that space, right? And any object then traveling on that space is going to be affected by the fact that you put a basketball in the middle. Say you then started rolling a marble along it, that marble is going to spiral in towards that basketball. And he said that's how we can think about gravity. Gravity is just caused by objects bending space-time. And then any object traveling on that space-time is going to be affected by the resulting curved nature of it. That meant that light traveling across space-time would also be affected by the fact that it is curved. It's going to be affected by gravity. So a couple months after Einstein published his theory, a guy called Schwarzschild came up with the equations that you would need to describe gravity around objects in Einstein's spacetime. And then a couple people noticed something a little bit weird, that there would be this Schwarzschild radius, a point in the equations where some of the terms went to infinity if you had a big enough mass, i.e. gravity itself could become infinite. And they called that sort of point a singularity. And they thought it was really weird and really strange, and therefore something was wrong with the equations. And scientists like Eddington and Lemaitre spent most of the 1910s and the 1920s trying to explain away those singularities in Schwarzschild and Einstein's picture of general relativity. So in the 20s, focus shifted to cosmology, i.e. understanding how the universe came to be and what had happened to it since then. And so Friedman, Walker, and Lemaitre all showed that if you took Einstein's theory of general relativity, you could show that the universe was expanding. Now, Einstein hated this. Everyone thought that the universe was static, and so that's the point where he came up with his idea of a cosmological constant to try and add an extra term to his equations and explain away the fact that it showed that the universe was expanding, rather than accepting it, which is what he should have done, because later on in the decade, in 1927, Lemaitre derived, and then Hubble in 1929 showed with observations that the universe was expanding. So Hubble, again using the telescopes at the Lick Observatory, and again observing these spiral nebula, he measured the distances to them and saw, first of all, that they were so much further away than the furthest star in the Milky Way. And then second of all, that the greater the distance they were at, the faster they were receding away from us. And so the idea of the Big Bang and modern cosmology as we know it was born. So this is where nuclear physicists come in. So a guy called Chandrasekhar in 1931 was studying white dwarfs. Now, white dwarf is what you get when a star like the sun runs out of fuel and dies, and it's sort of the leftover product. It's sort of an inert core of like carbon, nitrogen, and oxygen. It's held up by what's called electron degeneracy pressure. So basically, you've taken all the space in an atom, you know, the central nucleus of protons and neutrons, and you've taken the electrons and you've squashed all the space out of it until the only thing that's stopping you from squashing it more is the fact that the electrons are all negatively charged and so repel each other. Now, Chandrasekhar said, if you look at the equations for that, there is a limit above which those solutions are no longer stable, and you'll end up collapsing the star because you can finally overcome that force between the electrons. Now, Eddington and Landau argued, no, that's not physically possible. There must be some unknown mechanism that would stop the star from fully collapsing that we just don't know yet. Now, they were right, because a white dwarf would first of all collapse into a neutron star. What you have in a neutron star is that you force the electrons and the protons to actually merge together to become neutrons, so that all you're left with is neutrons as densely packed as they physically can be. Now, Zwicky and Bade in 1934 had suggested that maybe a neutron star could be the leftover product from a supernova, which is when a star more massive than the sun runs out of fuel, explodes, and dies. But they were considered completely hypothetical. But in 1939, that didn't stop Tolman, Volkov, and Oppenheimer from actually looking at the mass that a neutron star could be stable up until. They found the same thing that Chandrasekhar did. Up until a certain limit, you actually can't support the star any longer, and beyond that, it would collapse. But research sort of stalled there, and that's because the nuclear physicists were recruited to work on the atomic bomb projects of World War II, including Oppenheimer, who headed up the Manhattan Project in the 40s. And so the focus turned back to that weird emission seen in the spiral galaxies by Faith back in 1909. And a guy called Seifert in 1943 published a result where he'd said he'd observed 6 of those galaxies with the weird emission coming from their centre. And he saw that in a couple of them, yes, there was narrow emission, like we'd expect, but there was also this emission that had been smeared out or broadened. And now Seifert attributed that to a Doppler shift, i.e. the gas that's giving off that light is actually moving, some of it towards you and some of it away from you, and so it's stretched to different colours or different wavelengths, and you see that as sort of a smearing out. Now, even though those Doppler shifts were huge, which would mean that the object that the gas was going around would also be huge in mass as well, it didn't really kick up a lot of interest. Now, also in the 40s is when radio astronomy really kicked off as well. So the groups in Australia at CSIRO and in Cambridge and in Manchester were all set up towards the end of the 40s, and they started surveying the sky in radio waves to see what they could find. And so with these maps of the sky in radio, they started to see lots of pinpricks and very bright patches of radio in the sky that also were quite variable in their brightness as well. And so that kicked off a hunt for the optical or the visible light counterparts for these objects that were also going in the radio. So that by the time we got to the end of the decade in 1949, Bolton, Stanley and Slee had managed to find 3 optical counterparts for the radio sources that they'd seen. One was the Crab Nebula, or Messier 1, which was known to be a supernova remnant because the supernova had actually been seen by astronomers on Earth back in the 11th century. The other was M87, which is the biggest elliptical galaxy known at the time. The brightest radio source was NGC 5128, which we now know as Centaurus A. So throughout the 50s, this search for the optical counterparts of the ever-growing number of radio sources we knew about in the sky continued. So Baden-Minkowski in 1954 found that one of the brightest radio sources, Cygnus A, was actually coincident with a pair of merging galaxies. And that kicked off not just the search for the counterparts, but also a comparison between the shapes or morphologies of the things seen in the radio and the things seen in the optical. Because the weird thing that people were seeing was that once you found the optical counterpart to the radio source seen and they were compared, the optical counterpart was in the middle, and then you had 2 lobes of radio emission either side, as if they'd been ejected out of the plane of the galaxy. And so by the end of the decade in 1959, Burbage had managed to link a theory that was proposed by Kuypenhel back in the 1950s, that charged particles moving in a very strong magnetic field along a curved path could emit radiation. It was something called synchrotron emission. And so Burbage suggested that was how the energy was being produced in these radio lobes either side of the galaxy. So throughout the 60s, theorists are still puzzling over singularities. So whilst they were still puzzling, all the observational results were still flowing in, and I mean a lot of them. So Minkowski at the early 60s was still pioneering this work of finding optical counterparts to radio sources, and so he was taking spectra again of the light from the galaxy. The emission lines that he was seeing were at no known wavelengths, and so that suggested that either the object was incredibly distant, like the most distant thing that had ever been seen. He actually said at a conference that there is a remote possibility that it was a galaxy of stars in its own right, but that it was more likely that it was something in our own Milky Way with weird properties that we've never seen before. In 1963, Hoyle and Fowler suggested that there might be such a thing as a hydrogen-burning supermassive star. That would be a star that would be about 10,000 to about 1 billion times the mass of the sun that could still be doing nuclear fusion and burning hydrogen into helium. Richard Feynman then came along and said, no, that couldn't possibly happen because that thing would be so massive and dense that it would become a black hole and it would collapse in on itself. Around about the same time, in 1963, a guy called Schmidt looked at the spectra of the optical counterparts that they found for some of their radio sources and found that even though the emission lines were at very weird wavelengths, they had a pattern that was very similar to the hydrogen Balmer series that you could see in nebula in the Milky Way and then also in the lab with a hydrogen lamp and a spectra. But if that was the case, that would have put the object at an incredibly massive distance. It was actually 10 to 30 times brighter in the optical than had ever been seen in any other galaxy before. And so despite the fact that that was a convincing argument in terms of the spectral lines, people didn't understand how anything could be so bright until Salpeter in 1964 and also Zadovich in 1964 both suggested that you could get that massive optical brightness if you had matter falling onto a black hole and being accreted. And it could explain the brightness of these objects that were being seen by Schmidt and Minkowski that had been dubbed quasi-stellar objects. Then Ryle and Longhair in 1967 said, well, we could explain the radio emission if it was ejected at close to the speed of light. But they didn't know any object that was energetic enough to actually eject particles from an entire galaxy with that speed. Now, also in the 60s, X-ray astronomy has also kicked off. Now, X-ray astronomy can't be done from Earth because the Earth's atmosphere absorbs X-rays, so you've got to launch satellites and rockets into space in order to be able to do that. So Giacconi et al. In 1962 were one of the first to do this. They launched a rocket from New Mexico in the USA, and they mapped out sort of a general X-ray background on the sky, along with detecting X-rays from the centre of our own galaxy. So that by the end of the 60s, the likes of Bauer, Friedman, Byram, Compton, Mack, they'd all found X-ray sources in the Crab Nebula again, M87, the giantest elliptical galaxy known, the centre of our own galaxy in the Milky Way, and also the object that Minkowski was looking at the beginning of the 60s. They just didn't know what object was powerful enough to produce X-rays, some of the most energetic radiation there is. So at this point in the 60s, the ideas were out there, but they weren't really fully formed yet. What it took was the discovery of pulsars in 1967 by Jocelyn Bell Burnell and her PhD supervisor Hewitt. They were searching through radio data and found these regularly pulsing objects that at the time were thought even to be aliens, little green men. They were dubbed LGMs. What it turned out to be were rotating neutron stars. Now, the neutron star is no longer a theoretical object, and if the neutron star is not theoretical, then maybe its collapse into a black hole and a singularity isn't hypothetical either. Then in comes Stephen Hawking, along with Roger Penrose. And in the late 60s, they finally explained that singularities in Einstein's general relativity are actually to be expected. They are physical entities, and they shouldn't try to be explained away as mathematical curiosities. And therefore, since neutron stars were also now accepted as real objects, black holes also came to be accepted, at least in the theoretical community, as a real object. So that prompted Lyndon Bell, at the end of the decade in 1969, to build on that work from 64 by Salpeter and by Zeldovich to say that accretion onto a compact object could be the powerhouse behind optical light seen in quasars, the radio emission, the X-ray emission, and that also that modern day galaxies were the relics of quasars. They were dead quasars where the accretion has stopped and all that you're left over with is a supermassive compact object in the centre, or a supermassive black hole. So at the beginning of the 70s, Lyndon Bell and Rees in 1971 suggested that the Milky Way could actually hold a black hole at its centre. Now this is because the Milky Way was seen to be very dusty and giving off a lot of infrared light in its centre. And that had also been seen in the high redshift quasars that were beginning to be thought of as black holes. So it took until 1974 for Ballack and Brown to show that there was actually radio emission coming from the centre of the Milky Way, and that it was actually synchrotron emission as well. So combining that with Lyndon Bell's hypothesis at the end of the 60s meant that that radio detection was the first indirect evidence that we had for a black hole at the centre of the Milky Way. And then at the same time, Hawking, this time along with Bardeen, Carter, and also James Bekenstein's work, had also showed that you could describe a black hole in the same kind of way as thermodynamics, that it was radiating energy with a sort of temperature that was proportional to the black hole's surface gravity. At the end of the decade in 1978, a guy called Sargent started to look more closely at M87, the most massive elliptical galaxy known, and he looked at the central stars in M87 and how fast they were moving, and found that given how fast they were moving, they had to be orbiting an object that was about 1 billion times the mass of the Sun. So through the 80s, focus turned to these massive central objects in galaxies like what Sargent had found at the end of the decade. And observers throughout the decade referred to them as massive dark objects, or MDOs, whereas theorists were much more likely to refer to them as black holes, because it was sort of more accepted theory that they existed, but hadn't actually been observationally seen yet. And also because there was a lot of debate still about whether it was one single object that was at the centre of these galaxies, or whether it was sort of a swarm of very dense objects, like a swarm of black holes. And so throughout the decade, people were trying to get a better estimate for the masses of these things. So in 1984, Dressler measured the massive dark object in the centre of the Andromeda Galaxy and found that it was 10 million times the mass of the Sun. And then Cormandy in 1988 did the same for the Sombrero Galaxy and found that it was 1 billion times the mass of the Sun. And so the idea that these massive dark objects might be in the centre of nearly every galaxy started to take seed. So at the start of the 90s, first of all, I was born, but also this idea of whether the massive dark object in the centre of galaxies was a swarm of black holes or a single massive black hole kept people busy. And so it wasn't until the launch of the Hubble Space Telescope and the use of radio interferometry actually allowed us to be able to show it was a single black hole. Now in radio interferometry, you use massive radio telescopes that are separated by hundreds of miles so that you act as one single giant telescope so that you can see much more detail on the sky. And so Hans et al. In 1994 took a spectra using the Hubble Space Telescope of M87 and showed that the mass at its centre must be about 1 billion times the mass of the Sun, but in an area that was about 0.25 arc seconds across in the very centre of it, which would be a very small area to have a cluster or a swarm of black holes. And the nail in the coffin really was the work by Mayoshi et al. In 1995, who, using the VLBA, which is one of these radio interferometers, found that in Messier 106, there was a compact object of about 10 million times the mass of the Sun within about 1.3 parsecs, which is about 0.42 light years or 26,000 astronomical units, i.e. 26,000 times the distance from the Earth to the Sun. And so that was just far too much mass in too small of an area for it to possibly be a cluster of black holes, just because of the amount of collisions that would happen in such a tiny space between those black holes. And so the only viable object for these massive compact objects in the centre of these galaxies was a supermassive black hole. The things that Seyfert had seen, the radio emission, the X-ray emission, it all had to be coming from supermassive black holes. And so work by Hott in 92 and Urey and Padavani in 95 actually managed to unify our picture of these active galactic nuclei. And so what they said is that all of the active galaxies that we'd seen were powered by accreting supermassive black holes. It all just depended on the angle that you saw it at, because the way that black hole was accreting the material was in a very thin disk around it. And so depending on whether you were seeing that face on, edge on, would depend on whether you would see the narrow emission, the broad emission that Seyfert see, the radio emission, the X-ray emission, and so brought together our big picture understanding of what was powering all of these different objects. So the 2000s saw the advent of the idea that there are supermassive black holes in the centre of every galaxy. And that really came about because of the amount of surveys that were launched in the 2000s. So you had optical surveys like the Sloan Digital Sky Survey, you had infrared surveys like WISE, X-ray surveys such as ROSAT, all of which just boosted our numbers of active galaxies that we knew about up to about 100,000 throughout the 2000s. So because there were so many more active galaxies to work with, it meant that people could build on work in the 90s that was done by Magorian and Faber, showing that the mass of the black hole might be proportional to the brightness of the galaxy it was in. It meant that Fariz and Merritt in 2000 and Gebhardt in 2000 could show that actually the mass of the black hole is proportional to the mass of the bulge at the centre of the galaxy as well. As the black hole grows, the galaxy also grows too. And so it suggested that a black hole might be a key component of every galaxy, not just active galaxies. And so before this, the focus really was on understanding active galaxies separately from other galaxies, whereas now the focus has shifted to how the two objects co-evolve together throughout their lifetimes, which coincidentally brings us up to what I'm working on right now. So now the focus is very much on understanding the physical mechanism that's actually growing black holes in galaxies at the same time. And now earlier on in this decade, a lot of weight was put towards mergers of galaxies. Now mergers of galaxies are known to build up the amount of stars that live in the central bulge of a galaxy, kind of like the yolk of a galaxy, because of all the distribution of angular momentum that sinks the stars to the centre. Mergers drive the evolution of both galaxies and black holes. However, my recent work has shown that that might not be the case. So this is work by Simmons, Smethurst and Lintop in 2017 that showed that galaxies that don't have that central bulge component still had supermassive black holes that were as massive as the kind of things that were seen in M87, the biggest elliptical galaxies known. And so if the galaxies didn't have a bulge, then they hadn't had a merger. So how else had they grown? So then we had a chat with some friends in theory who ran some simulations, and then in work by Martin et al. In 2018, published that actually only 40% of the mass that's currently contained in all of the supermassive black holes in the universe can be attributed to mergers of galaxies. The other 60% is not from mergers at all, and that the mechanism that might be powering that coevolution of growth of black hole and growth of a galaxy might just be a galaxy internally driving gas into the centre of that supermassive black hole. So I'm just glad that I get to be this tiny piece of this jigsaw puzzle of the understanding of supermassive black holes. Because although this might feel like the end of the story now, I can tell you it most definitely isn't. So if a neutron star is no longer so through the 80s, spit it. So now in the tensies, the noughtsies, the tensies,